And so you conjecture that, and then I try to think about this, and it actually turns out that you can strengthen this a little bit. So if you define this first letter statistic, then what you can say is this quintuple, adjacencies, descents, first letter, major index, and stat have the same distribution as when you switch the major and stat. So there's an involution that fixes adjacencies, descents, the first letter, and switches the major index and the stat. And I think it's not so much this fact as the bijection that does it. I'm not sure what would the bijection be that you get with with a computerized proof, but I think this one is very nice because it's just so simple. It's almost basic. So here's the boring definition of this bijection. It looks like that. It's hard to see what's going on, but if you think about these reversal complement and reversal complement symmetries, then what you're doing is, right, pi has this first letter, and then there's the top sequence, everything above k, and everything in the bottom sequence, everything below k. So what you're doing is you take the complement of top and bottom separately, but you take the reversal of the whole thing together. And alternatively, you can insert bars like this. So 5 goes into 4, 3, so we put a bar here, and then we go up to 6, a bar there, bar, go down to 1, up, down, and we put a bar as soon as the maximal block stops. And then you take reversal of complements with bars and read it back as a permutation. And that gives this bijection. So it's an involution, and it's almost basic because it just has to do with reversals and complements. And so this is the one that does the trick. So it's pretty straightforward to see that with the adjacencies and descents, and well, first letter is preserved. That's just that's obvious. Adjacency descents are also pretty easy to see. And as far as major, the fact that it switches major and stat can be seen from, well, you can't prove this directly, but you can show that the sum of maj and stat in any permutation pi is equal to this, which is also the sum of major and pi, major pi prime. And the way you do this is, again, well, it's just an example, everything's worked out. And I guess there's one thing I want to mention. See, there's 5 goes to 4, that's the extra adjacency that doesn't seem to be here, but remember when you put a 0, right? When you put a 0 after 1, that gives you the extra adjacency that wasn't in pi. So if you look at those at those sums of pattern statistics, then what you have is you're counting descent top and bottom, everything above descent top, everything below descent bottom, and it's almost as if you're counting everything in between descent top and descent bottom if those were reversed. So what you get is you can just write it like this, and to figure out what this difference is, you want to write inversions in 2 ways. So think of these inversions. Either these elements are consecutive, or you can insert something to the left of the right of the larger element. On the other hand, either the larger element is the first, or you can insert something to the left of the larger element, and then subtract, and this is what you get. This bracket means that the 2 is the first letter in the permutation. So what you're counting here is everything that's less than the first letter. On the other hand, to get the other sum, what you do is think about the positions of descents in pi and pi prime. So when you add them up, descents within the top and the bottom go to descents within the top and the bottom, and ascents across the first letter go to descents across the first letter. So I should sort of put the shadow of this letter to the right, so you can see. So you can count in pi prime, you count the same positions from the right, because remember you reverse the whole thing, but then take the complement separately. And each descent within the bottom or the top permutation that doesn't go across the first letter contributes exactly all the letters in this permutation. If you just use the same pattern, right, this pattern occurrence statistics, it turns out you're counting all the letters of this permutation together with this shadow letter K for every descent within the bottom and the top. And for every descent that goes across, for every pair of descent across K, something in part of a bottom permutation, and then ascent across K, what you're counting in the sum of major index of phi plus phi prime is all the letters except these at the bottom. So you're just counting all n plus 1 letters every time for every descent, except the length of all the blocks, which is exactly the number of letters below K. So that's basically this map. I guess I just maybe I thought of what kind of conclusion to draw from this, and it's that I think that the computer algebra is something. It's like this autopilot does everything for you. It's like the driver that drives you everywhere you want. So all you have to do is drive for pleasure, and that's what it really is. One question is I have is this is such a pretty map that I wonder, is it like a one-trick pony, or does it have any other interesting properties? Is it only good for this, or maybe they're good for something else? And then there's some analogs in permutation tableaus that maybe you can extend to those triples, and I'm not sure how, and then you can just continue. There's a whole lot of them. So there's my little handmade present. Happy birthday.
Questions?
So in particular, you prove the conjecture of Erickson?
Yes.
Yeah, no, it's beautiful. But more generally, you added more statistics.
No, it was this more just than say in evolution. That's why more statistics the first letter.
Yeah.
Any other questions? Let's thank the speaker again.